In this video, we're going to continue talking about Lewis dot structures. This is because there are a few things that we still have to talk about. One of them is the Lewis structures for polyatomic ions. So this means that we'll have to calculate the formal charge, which is the charge on each individual atom, which is calculated by taking the number of valence electrons for that atom, subtracting off the number of lone pair electrons on that atom while it's in the molecule, and then subtracting off the number of bonds going to that atom. And that will give you the formal charge for the atom. And we'll also need to talk about the formation of double bonds in our polyatomic ions. We also need to talk about Lewis structures for atoms that can break the octet rule. So this is pretty much everything except carbon, nitrogen, oxygen, and fluorine. So some atoms will have less than a full octet. So that's pretty much anything up to boron. So that'll be hydrogen, helium, which we don't really care about because it doesn't form bonds, beryllium, and boron. And then other atoms can have more than a full octet. And so that's pretty much anything after aluminum. Then we also need to talk a little bit about resonance structures. And this is because there are multiple equivalent structures that a lot of these can have, and that's based on the orientations of the double bonds. And so we'll talk a little bit about that. So exceptions to the octet rule, so like I said, there are atoms that can have less than 8, so things like hydrogen, beryllium, and boron are kind of the ones that we're interested in here. But then there are atoms that can have more than 8 electrons around the essential atom. So the ones we'll be mostly talking about are sulfur, phosphorus, chlorine, bromine, and iodine. These can have 8, 10, 12, or 14 electrons when they are the central atom. And what we'll find is that when they are breaking the octet rule, the number of bonds plus the number of lone pair electrons will be equal to the number of valence electrons of a neutral atom. And we'll see how that looks here in a little bit. Sulfur, phosphorus, and chlorine, bromine, and iodine, though, can only have 8 electrons when they're a terminal atom. So this breaking of the octet rule happens when they're a central atom. When they're a terminal atom, they will still follow the octet rule. So let's look at a few instances of these atoms breaking the octet rule. If we draw the structure of sulfur hexafluoride using Lewis theory, we would end up with this. So we have sulfur as the central atom, 6 fluorines around it, each of them with their full octet, and we see sulfur has 6 bonds to it. So sulfur has 6 valence electrons, so it can have up to 6 bonds. So remember, the number of bonds plus the number of lone pair electrons will be equal to the number of valence electrons it has as a neutral atom. If we look at this for phosphorus pentachloride using Lewis theory, we would get something that looks like this. And phosphorus has 5 valence electrons, so it can have 5 bonds. And if we look at boron trichloride using Lewis theory, we would get something that looks like this. And boron has 3 valence electrons, so it can have 3 bonds. Then something like the perchlorate ion, we would get something that looks like this. And chlorine has 7 valence electrons, so it can have 7 bonds. So now, if we want to look at some of the things that are going to be different when we're drawing these Lewis structures, the process is pretty much the same as what we saw before in the previous video, but now we have a few extra things. So the first one is that when calculating the number of electrons, we want to add an additional electron for every charge on the polyatomic ion. So if a polyatomic ion has a -2 charge, we would need to add 2 extra electrons into our electron count. The second thing is that after making this structure, we need to calculate the formal charge on each atom. So remember, formal charge is going to be equal to the number of valence electrons on the neutral atom minus the number of lone pair electrons minus the number of bonds. Then we also want to reduce the charges on each atom as much as possible. So after we calculate the formal charge, we'll find that a lot of the atoms have a charge. We want to reduce the charges as much as possible. So we want each atom to have as little charge as it can possibly have. So if the central atom cannot break the octet rule, if it's something like carbon, nitrogen, or oxygen, but it does not yet have a full octet, then just as before, we would form double bonds to reduce the charges until the central atom has a full octet. But if the central atom can break the octet rule, then we form double bonds until the central atom has a number of lone pair electrons plus a number of bonds that's equal to the number of valence electrons in the neutral atom. So let's look at this using the carbonate ion. So when we calculate the number of electrons, We do 4 for the carbon. There's only 1 carbon. There are 3 oxygens. They have 6 valence electrons. Then we need to add this extra 2 here because it has a -2 charge. So this would have 24 total electrons. Carbon will be our central atom. We put the oxygens around it, put bonds to it, we put our lone pairs on it, and then we calculate what the formal charge is on each atom. So remember, that's the valence electrons minus the number of lone pair electrons minus the number of bonds. So we calculate it this way for each atom. The oxygen has 6 valence electrons when it's neutral. We subtract off the 6 lone pair electrons on each one, and then minus 1 bond, because they each have 1 bond. That gives -1, so they have a charge of -1. The carbon has 4 valence electrons. It has 0 lone pair electrons and 3 bonds. So it has a charge of +1. So we put those charges next to each atom like that. So this is very important. You want to make sure that you're putting the charge next to the atom like that. So each oxygen has a negative charge and the carbon has a positive charge. But now we want to reduce the charge as much as possible. So we see the carbon does not yet have a full octet, so we can form double bonds to it. So we can get rid of one of the negative charges and the +1 charge on the carbon by forming a double bond. So we do this, but now we see that the carbon has a full octet, so we cannot form any more double bonds to that carbon. And what we see is that we can have what are called resonance structures for this carbonate. So there are 3 possible ways we could have drawn this, and all of them are equivalent, and these are called resonance structures of each other. So the ion has resonance. We're not really going to get into sort of the quantum mechanical interpretation of this, but we can say that these are all equivalent, and so all of them are correct. So now let's look at this for the sulfate ion. We have 6 valence electrons on the sulfur, 6 on each of the 4 oxygens, and we have a -2 charge, so we have to add +2 extra electrons. The sulfur will be our central atom because it's lower than oxygen on the periodic table. We'll put our oxygens around, form the bonds, put the lone pairs on it, and now we want to calculate the formal charge on each of these atoms. So the oxygen, we do 6 valence electrons minus the 6 lone pair electrons minus 1 bond. They each have a -1 charge. The sulfur is 6 valence electrons minus 0 lone pair electrons minus 4 bonds, so it has a +2 charge. We want to put the charges next to the atoms like this. But remember, the sulfur can break the octet rule. So we can actually start forming some double bonds in order to reduce these charges as much as possible. And we can do this up until the sulfur has up to 6 bonds because it has 6 valence electrons. So when we do that, we get this structure right here. So 2 of the oxygens now have double bonds to the sulfur. And this one also has resonance structures. So these are the 6 possible resonance structures for it. So again, these are all equivalent structures. They're all correct answers to drawing the Lewis structure for sulfate. So let's do this for nitrate. So again, we want to add up all the electrons. We add +1 because it has a -1 charge. The nitrogen will be our central atom because it's closer to the carbon column. We put the oxygens around, put the bonds, put the lone pairs. Then we want to calculate the formal charge on each atom. So we do that for the oxygen, we get -1. For the nitrogen, we get +2. So we want to reduce these charges as much as possible. We see that the nitrogen does not have a full octet. So we can form a double bond between the nitrogen and one of the oxygens. So we get this structure. And so we see that this structure has a +1 and a -1 and then another -1. So the +1 will cancel one of the -1s. We end up with a net -1 for the charge on it, which would make sense because our ion has a negative charge on it. And this has a full octet on the nitrogen now, so we can't form any more double bonds. And again, this will have multiple resonance structures. These are all equivalent structures. And here are some practice problems. I encourage you to work on these before you watch me go through the answers. So for the first one, we have the sulfur trioxide, and when we draw the Lewis structure for this, we get this structure. And sulfur has 6 valence electrons, so it can have up to 6 bonds. Then we want to do the structure for the chlorate ion. So we can have this structure, or this structure. So again, these are all equivalent. These are resonance structures, and we see that chlorine has 7 valence electrons, and so it can have 5 bonds plus 2 lone pairs going to it. Then we want to do the nitrite ion, so this is NO2 minus. We can have this structure or this structure. Those are equivalent structures, and this one does not have the expanded valence. It does not break the octet rule, so we don't have to talk about how many additional bonds it can have. But then when we want to draw every equivalent structure for phosphate, again, we will end up with multiple of these, so this will be one of them, this will be one of them, this will be one of them, and this will be one of them. And phosphorus has 5 valence electrons, and so it can have up to 5 bonds. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.